Okay, so for this question, we have a family of differential equations parameterized by lambda, like so, and we want to find the plot lines, the bifurcation values, and then to sketch the bifurcation diagram based on values of lambda. That would make more sense. All right, so the first thing we want to do is find the critical points, right, or the equilibrium points for this equation. And the way to do that is to set y prime equals to 0 and then to solve for values of y. So if we do that, we get three different values of y, depending on what lambda is. For equilibrium points, y is either equal to negative lambda over 2, 0, or lambda over 2. What now? We want to plot the phase lines for this equation. So what that means is if we think about a number line here of y, and we put 0 in the middle, we put negative root lambda over 2, and then root lambda over 2. Now we know that these are the critical points for y. So what that means is that if we consider the graph of y, then at these 3 points, with the direction of y change. So if we have negative root lambda over 2, 0, and then root lambda over 2, then it could look something like that, for example. So that at these 3 points, the direction of y lambda changes. So we can find out what direction each of these parts are by plugging in points in between each of these ranges to our original equation, which is y prime is equal to lambda minus 4y squared times y. So what that means for us is, for example, we have lambda is equal to negative 2, negative 1, 0, 1, or 2, right? So the first thing is that if lambda is negative, we can't take a square root of it. So these two don't even exist. So dne does not exist. For 0, then these two square roots also become 0, so we only have one critical point, which is 0. For 1 and 2, we get the values for our critical points to be negative 1 half, 1 half for lambda is equal to 1, or negative root 2 over 2, root 2 over 2 for lambda is equal to 2. What that now means is we have to choose four points here such that we can plug it back into our original equation and see if y prime is positive or negative, and that'll tell us if y is either increasing or decreasing in that range. So we see that here we can choose negative 1 and 1 because our largest values, our most further out values of critical points are these two, and root 2 over 2 is less than 1. Root 2 over 2 is less than 1, and then same for negative root 2 over 2. And then similarly here, we can choose 1/4. And that makes sure that we're closer than these two critical points even for lambda equals 1. So now what we have to do is we have to plug in these two for each of these. So if we have y prime is equal to lambda minus 4y squared times y for just to make it a little bit easier, let's do our calculations with y is equal to these values because these are the values we've chosen. But also let's do lambda is equal to 1 just to make our calculations a little easier. So if we plug in here with lambda equals 1, we get okay. So what that means now is if we go back to our number line up here, our value for negative 1 was 3, which is positive. So we can put a big positive here. And then this was negative 316, so it's negative. This was positive 316, so it's positive. And then this was negative 3, so it's negative. So what that means is that since it's positive in this range, that means before this critical point, our function for y is increasing. So I'll put our greater than symbols because it's increasing. And then so same for here, we have it increases between 0 and root lambda over 2. But then for negative, it's the opposite. So it's decreasing here. This is basically what our phase diagram is. So let's just redraw it. We'll just draw it right here. So here, for root lambda over 2, the points around it. So here, these are increasing. So it goes closer to root lambda over 2. And then the points above are they're decreasing. So they also are decreased to root lambda over 2. So what that means is that this is stable. This, on the other hand, the points around it, they go away. And the points around here also go away from 0. So it's unstable. And then similarly for this point, negative root lambda over 2, the points are decreasing, so it gets near it. And below that value, the points are increasing, which means that this one is also stable. So this is if our value for lambda is equal to 1 or 2. Because if lambda is equal to 0, then we only have one critical point. We have 0 here. And what happens around it? Well, if we just use our values for 1 and negative 1 here, then we have values around it going near it, and then values above it going below, because here the values will be decreasing and here will be increasing. So it will be stable. And then this is similar for negative 2 or negative 1. Since the other two don't exist, they basically collapsed into this 0. A bifurcation point. So what is a bifurcation point? A bifurcation point is where critical points come together. As lambda changes, the number of critical points change and they converge to some point. For example, here, like as lambda is less than or equal to 0, we only have one critical point. Only y is equal to 0. But if lambda is greater than 0, we have y is equal to 0 or negative, positive or negative root lambda over 2. What that means is that since y equals 0 shows up in both of these, as lambda becomes positive, the number of critical points expands from 0. Y equals 0 is a bifurcation point. A bifurcation point is where critical points come together. If we wanted to graph a graph, which we do, like so, and we want our graph to be of our critical points, y critical points, and our values of lambda. So if lambda is 0, negative 1, or negative 2, then the only points we have are zeros for y. And then even for 1 or 2, we still have 0 for y as a critical point. But for positive and negative values, we also have other values. We have 1/2, negative 1/2, root 2 over 2, negative root 2 over 2. So what this means is that our overall bifurcation diagram is going to look something like this, where we have y equals 0 as a critical value always, and then two more branches of critical points depending on what your value of lambda is. So this is our bifurcation point. And this is your bifurcation diagram. And one thing to note is that This kind of bifurcation point is called a pitchfork bifurcation. And I think that's it. Let's take a look at the question. So we plotted the phase lines, which is right here. Right, this is plotting the phase lines. We classified them based on if they're stable, unstable, or yeah, if they're stable or unstable. And we found the bifurcation values and sketched the bifurcation diagram. So yes, we're done.